Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on prime factor trees. So prime factor trees are used to write composite numbers as the product of primes. So remember, we went through this terminology last time. A composite number is a number that has more than two factors, like 14, 28, 34, 51, whatever. A prime number has only two factors, like 11, 13, 41, etc. It turns out we can write any composite number as a whole heap of prime numbers multiplied together. So for example, 30 is a composite number that has heaps of factors. We can write it as 2 times 3 times 5. 2, 3, and 5 are prime numbers. So I've written 30 as some prime numbers multiplied together. I can do the same for any composite number. 63 is a composite number. It is divisible by 3. So that means it has a factor other than itself and 1. So it must be composite. So I can actually write it as 3 times 3 times 7. So 3 prime numbers multiplied together, or if you like, I can write it as 3 squared times 7. Sometimes there will be heaps of prime numbers in this multiplication. Sometimes there will be not many. So for example, 64, I can write it as 2 to the power of 6. 2 times itself 6 times. So all of these numbers here are prime numbers. So we want to be able to take a composite number and find these prime numbers. That will help us with things like highest common factor, lowest common multiple. This is a very important concept in maths. Just as like amino acids are the building blocks of proteins, prime numbers are the building blocks of integers. Okay, so how do I actually find this? How do I get a number like 30 and find the prime numbers that I can multiply to get it? Well, I actually use prime factor trees. So let's look at 30 and we'll draw a factor tree for it. So what we want to do is we want to factorize 30. We want to write 30 as the product of any two numbers at this point. Doesn't matter whether or not they're prime. So you can do this in a number of ways. You can write 30 as 10 times 3, 15 times 2, 6 times 5. It doesn't actually matter which of those you choose. So let's say, for example, I choose to write 30 as 10 times 3. So I factorized 30. Now, 10 is not a prime number. It's composite, but 3 is. So what I'm going to do is another step. I'm going to leave the 3 alone because it's prime. And what I want is just prime numbers that multiply to 30. So the 3 is good. I'll leave it as it is. 10, however, is not prime. So I'm going to factorize 10. So 10 is 5 times 2. So I write it like this. Now 5 and 2 are prime numbers. So you can see here I've got 30 equals 5 times 2, which is 10 times 3, which is exactly what I had up here. Now I just want to show you it wouldn't matter if I chose different factors originally. So if I started with 30 and instead of going 10 times 3, let's say I went 15 times 2. Well, I can follow the process and get the same answer. 2's a prime, so I stop there. 15 is composite, so I write numbers that multiply to 15, in this case 5 and 3. So these two answers are the same because, of course, it doesn't matter the order in which you multiply. It doesn't matter if you go 5 times 2 times 3 or 5 times 3 times 2. You still get to 30. So that's how I got my prime factorization here for 30. So let's look at how I would get it for 63. Well, I'm going to do the exact same process. I'm just going to find any numbers that go into 63 and then keep factorizing until I've got only prime numbers. So for 63, I can write it as 7 times 9. Once again, it wouldn't matter if you chose different factors here, like 21 times 3. So I've got 7 times 9. So then I notice that 7 is a prime, so I'll leave it as it is. 9, however, is not a prime. It's composite because it's divisible by 3. It's 3 times 3. So there we have it. I've got 63 equals 7 times 3 times 3, which is what I got here. So sometimes you'll be asked to write in expanded form. And sometimes you'll be asked to write in index form. So this is in index form because this little 2 here we call a power or an index. Remember, 3 to the power of 2 means you times 3 this many times. 3 times 3, 3 times itself twice is 3 to the power of 2. And this would work exactly the same for the number 64. It'd just take a little longer. So let's find factors of 64. Well, we should know it's 8 times 8. So 8 is not a prime number. So we're going to write it as the product of some other numbers. So 8 is 4 times 2. Okay, so we've now got some 2's that are prime. But 4 is not prime. It's composite. So I need to factorize 4. It can be written as 2 times 2. Okay? And so when we get numbers at the bottom, prime numbers, you multiply them together. So 2 times 2 times 2 times 2 times 2. 2 times by itself 6 times gives 64. I don't want to write 2 times 2 6 times. That takes too long. So just write as 2 to the power of 6. So this means I multiply this number 2 by itself 6 times. This doesn't mean 2 times 6. It means 2 times by itself 6 times. 2 to the power of 6 is 2 times 2 times 2 times 2 times 2 times 2. So, of course, to be able to do this, you need to recognize which numbers are prime and which are composite. So if you aren't quite there yet, go back to the previous lesson where we looked at the sieve of Eratosthenes. We listed all the prime numbers under 100 in that big grid. Of course, we're not going to do any numbers with prime factor trees that are so great that you'd need prime numbers more than 100. So just look back at the sieve of Eratosthenes. All right, thank you so much for tuning in. This has been the luckiest maths teacher in the world. Have a great day.